Hello learners, once again I welcome on the class of fluid mechanics. So I hope you all are safe and doing well. So in the previous discussion we have seen in laminar flow we have discussed the velocity distribution, shear stress, maximum velocity, average velocity and head loss in the two parallel plates which was fixed at a distance of h. So we have seen this terminology. So today I will discuss the same terminology I will derive for the in circular pipe. Like I will derive the general equation of velocity, and after that condition for the maximum velocity and the expression of maximum velocity, and after that I will derive the general form of shear stress equation, and after that condition for the maximum shear stress, and I will show you the distribution of shear stress as well as velocity distribution, and I will show you the nature of shear stress and the velocity distribution, and after that I will compute the average velocity and what is the head loss, and with the help of that head loss I will show you the how to compute the power, and after that I will discuss the Darcy's equation, how to compute the head loss by the Darcy's equation, and after that I will also discuss the friction factor, what is the value of Darcy's friction factor for the laminar flow and turbulent flow. Today I am discuss about the laminar flow in pipes. In the previous class we have seen the flow in the parallel plates when two plates are fixed and which is apart at a distance of h. So we have seen the various terms like velocity distribution, average velocity, maximum velocity, head loss, and the shear stress distribution and the maximum shear stress distribution. So same thing I will also discuss in the laminar flow in pipes. So let us assume this is our circular pipe and this is the center line. This is the flow, and let us assume this is our diameter of the pipe and this is the radius of the pipe. If I take an element, let us assume this is our element, which is at a distance of y, and this element having the radius r and the length is dx. So in the last class we have seen the pressure. Let us assume this is our pressure P. So here is P plus del P by del X into dx. Similarly, the shear stress can also be written. So velocity is constant, so acceleration is 0 because acceleration is rate of change of velocity. So force is equal to 0. So we can write P into pi r square, incoming force, minus P plus del P by del X into dx into pi r square minus tau into 2 pi r into dx is equal to 0. With the help of that we can compute the shear stress is equal to minus del P by del X into r by 2. So with the help of this expression we can say that the distribution of shear stress is once again linear, and the shear stress, so when r is equal to 0 means at the center line shear stress is 0, and when r small r turns to capital R means at the boundary of the pipe the shear stress is maximum. So with the help of Newton's law of viscosity we can write tau is equal to mu du by dy, or we can write mu du by dy is equal to minus del p by del x into r by 2, or we can write from this diagram y plus r is equal to capital R. So we can write r plus y is equal to capital R. So dr plus dy is equal to 0, means dr is equal to minus dy. So this is our equation first. So equation first can be written as mu du by dr is equal to minus mu du by dr is equal to minus del p by del x into r by 2, or we can write mu du by dr is equal to minus del p by del x into r by 2. So once we integrate, du by dr is equal to r by 2 mu, sorry it is positive, del p by del x. Integrating both sides, so we can write u is equal to r square by 4 mu del p by del x plus some constant c. So with the help of applying the boundary condition at r is equal to capital R, u is equal to 0. So constant value is coming from equation number 2 is equal to minus r square by 4 mu del p by del x. Putting the value of constant c in equation number second, so from second u is equal to r square by 4 mu del p by del x minus r square by 4 mu del p by del x. So if I take common, u is equal to 1 by 4 mu minus del p by del x, so it is coming r square minus small r square. So this is the expression of velocity, and the velocity is parabolic. For the computation of maximum velocity, at r is equal to 0, u is equal to u max. So the maximum velocity is equal to 1 by 4 mu minus del p by del x into r square. So this is our the maximum velocity in case of pipe flow. For the computation of mean velocity, similarly average velocity can be computed. Average velocity is equal to u max by 2, and the expression of average velocity is 1 by 8 mu minus del p by del x into r square. Similarly, mean velocity can be computed. Mean velocity or average velocity. So we have already written the expression of average velocity. So whether it is correct or not, this is the velocity distribution. This is our y. M dot is equal to 0 to r rho into u to 2 pi r dr. So it is coming rho into pi r square into u average. So u average is equal to 2 by r square 0 to r u into r into dr. So u average is equal to 2 by r square, u can be written as 1 by 4 mu minus del p by del x into 0 to r integral 0 to r r square minus r square into r dr. So average velocity is coming 2 by r square 1 by 4 mu minus del p by del x by r square 1 by 4 mu minus del p by del x into r4 by 4. So the average velocity is coming, expression of average velocity is 1 by 8 mu minus del p by del x into r square. So this is the expression of average velocity. So we can write u average divided by u max is equal to 1 by 2. Similarly, head loss can be computed. So in case of pipe flow, head loss. So average velocity is equal to 1 by 8 mu minus del p by del x into r square, or u average can be written as d square by 32 mu minus del p by del x. If I convert, r is equal to d by 2, so minus del p running from 1 to 2 is equal to 0 to L 32 mu by d square into u average into del x. So it is P1 minus P2 is equal to 32 mu into u average into L divided by d square. So we can write P1 minus P2 by gamma is equal to 32 mu into u average into L divided by gamma d square. and P1 minus P2 by gamma is the head loss. So head loss is equal to 32 mu into U average into L divided by gamma into D square. So this is the expression of head loss in case of flow in circular pipe. Similarly, power can be computed. So power is equal to gamma into Q into HL. So with the help of that, where gamma is the unit weight, Q is the discharge, and HL is the head loss. So in circular pipe laminar flow, what we have derived, velocity, expression of velocity is 1 by 4 mu minus del P by del X into R square minus R square. And the velocity, expression of velocity, so if I draw the velocity distribution, so when this is R, this is also R, this value is capital R. So when R is equal to 0, velocity is maximum, and when R is small r is equal to capital R, so velocity is 0. So this is the maximum velocity, U max velocity. Similarly, expression of shear stress, expression of shear stress tau. So tau is equal to minus del P by del X into R by 2. So if I draw the shear stress distribution, so when R is equal to 0, shear stress is 0. So this is the distribution of shear stress, maximum, 0. This is R, this is also R. Shear stress distribution, and the maximum shear stress is equal to minus del P by del X into capital R by 2. Similarly, we have derived the maximum velocity is equal to 1 by 4 mu minus del P by del X into R square. So this formula we have to remember, and average velocity is half of maximum velocity. So 1 by 8 mu minus del P by del X into R square. So this is the expression of maximum velocity. Similarly, head loss in the circular pipe is 32 mu into U average into L divided by gamma into D square, and the power is equal to gamma into Q into HL. So this is all about the circular pipe. Briefly, I will discuss the what is Darcy equation. In more detail, I will discuss in the pipe flow. So Darcy equation. So according to Darcy, head loss is equal to F into L V square divided by 2 into G into D, applied in laminar as well as turbulent flow. So this is applicable for both laminar as well as turbulent flow, where F is the Darcy Weisbach friction factor. Friction factor, and F dash is equal to F by 4, where F dash is equal to coefficient of friction. F dash is the coefficient of, so F dash is the coefficient of friction, and same thing, L is the length of the pipe, V is the velocity, and capital D is the diameter of the pipe. So L is the length of pipe, D is the dia of pipe. So friction factor in laminar flow, friction factor in laminar flow. So friction factor, we know that in laminar flow head loss is equal to 32 mu into U average into L divided by gamma into D square, and this is equal to FL V square by 2G into D. So we can write F is equal to 64 mu divided by rho into V into D, or we can write F is equal to 64 rho into V into D divided by mu, and this rho Vd by mu is our Reynolds number. So friction factor is equal to 64 by Re in case of laminar flow, but remember in mind that this formula is applicable for laminar flow only, and the friction factor for the turbulent flow will be different. So dear student, today I have discussed about the how to compute the general velocity equation, maximum velocity equation, and what is the average velocity, maximum velocity, and what is the nature of velocity distribution, and after that what is the shear stress expression and what is the nature of shear stress, and after that how to compute the head loss and what is the power. So these all things I have derived. The velocity distribution in a circular pipe we have seen 1 by 4 mu minus del p by del x r square minus r square, and the maximum velocity when small r is equal to 0, and the expression of the maximum velocity is 1 by 4 mu minus del p by del x into capital R square. Similarly, the average velocity is equal to the half of the maximum velocity, and the expression is 1 by 8 mu minus del p by del x into R square. And after that I have derived the by applying the Newton's law, and we have derived the shear stress equation, and the shear stress expression is minus del p by del x into R by 2. With the help of this R by 2 we have I have shown you that the nature of the shear stress is linear, and maximum shear stress is occur at the boundary of the pipe. And after that maximum shear stress is computed, and after that I have derived the head loss, and with the help of that head loss I told you that the power can be computed gamma q into HL, where HL is the head loss and Q is the discharge and gamma is the unit weight of the fluid. And after that I have discussed the how to compute the head loss by Darcy equation. So according to Darcy has given the head loss, major head loss, that is FLV square by 2 GD, or we can also write this head loss in terms of discharge, that is FLQ square by 12.1 d to the power 5, where F is the Darcy's friction factor, and L is the length of the pipe, V is the velocity, Q is the discharge, and D is the diameter of the pipe. And after that I I told you that there is a relation between the coefficient of friction and the Darcy-Weisbach friction factor. And for the laminar flow, I have derived the expression of Darcy-Weisbach friction factor, and for the laminar flow, I have shown you the expression, that is F is equal to 64 by Re, where Re is the Reynolds number. So in the next class, I will discuss problems related to the parallel plates and this circular pipe, and after that I will start the new topic related to the fluid mechanics. So take care of your health and happy learning.